In this lab, we're going to be using the absorption of light to make a calibration curve. So we need to understand complementary colors and the BEER-LAMBERT law. If we have a yellow drink or a yellow solution, the light that's passing through that solution is allowing yellow wavelengths of light to reach our eyes. It is not allowing other wavelengths of light to reach our eyes. If we look at the light that's being absorbed by the solution rather than the light that is being passed through the solution, then we could get something that looks like this scan. So this is called an absorption spectrum. So you'll notice here on the x-axis we have wavelength increasing to the right, which means energy and frequency are increasing to the left. And on the y-axis we have absorbance, which is a unitless measure of how much light is absorbed in the sample. So the light that comes through, some of it passes through on the other side, but some of it gets absorbed in the sample. How much is absorbed? And we can see here that from 900 down, there's no absorption in that solution, not even at yellow wavelengths, right? We said yellow wavelengths were getting to our eye. They're passing through the solution and being transmitted. So what is being absorbed is actually these other colors, the blue and purple colors, the wavelengths of light that are higher energy, and we see a high absorbance there. So if we want to predict which colors of light will be absorbed by a solution, then we want to consider complementary colors and the color wheel. So here's another set of absorption spectra. Again, we have the wavelength here on the x-axis that goes from 400 to 700. That's approximately the visible range. Again, absorbance is on the y-axis, and we can see again that yellow food dye is absorbing light in the blue and purple region. We can see that the red food dye is absorbing light in the green region. We can see that the blue food dye is absorbing light primarily in the orange region. And then the green food dye is actually a mixture of blue and yellow. Why does red absorb in the green? Well, if we look at the color wheel, the red food dye, what appears to be red and is transmitted through that solution, is actually absorbing green light, and that is on the opposite side of the color wheel. So when we talk about the yellow food dye, we said that that was absorbing blue and purple light, and that's because it's on the opposite side of the color wheel. Likewise, the blue food coloring is absorbing orange light down here, and that is on the opposite side of the color wheel. So the color wheel is a good way to predict which wavelengths will be transmitted or absorbed by a sample if you can see the color or if you see the absorption spectrum. The amount of light that's absorbed by any given sample, or the absorbance, is given by a capital A in the BEER-LAMBERT law. The BEER-LAMBERT law says that the absorbance, or the amount of light that is absorbed by a sample, is proportional and directly related to the molar absorptivity. This is a constant value. Although it is wavelength dependent, it is intrinsic property of the sample, of the molecules that we're interested in. The units for that are given in inverse centimeters inverse molar, so 1 over centimeter molar. B here is the path length, so how long is the light in the sample, right? Is it going through a millimeter of sample, or is it going through a centimeter or a foot worth of sample? And then C is the concentration of the sample, and we use that in molarity. So you can see units wise, if we have inverse centimeter, inverse molar, times centimeters, times molar, all of our units will cancel out, and absorbance is unitless quantity. In order to illustrate the BEER-LAMBERT law and its dependence on E, B, and C, I'm going to move to a PhET simulation to show you what that looks like. In this simulation, the link is posted for you on Blackboard, so you can check this out on your own if you like. We have a light source here. That's a laser that you can turn on. Right now it's a green laser. And you have a solution that you can change what the solution is. I'm just going to stick with the drink mix. And here's a detector, and we're going to measure absorbance. You can also measure transmittance. They're logarithmically related to each other. But we'll just stick with absorbance for now. We can measure the path length, which is set at 1 centimeter, and we can also change the path length. What's handy is to notice, right, based on our absorption spectrum from the slides on the previous slides, what looks like a red solution will absorb best in the green region. And we can prove that, right, by moving this little slider to a different wavelength. If we move it to a red wavelength, we can see that our absorption is very low, okay, 0.02, which means most of our light is getting through. Even yellow and orange light is still passing mostly through, 0.03. And as we move into the green, now we start to get significant absorption of light because it's on the complementary side. It's on the opposite side of that color wheel. If we continue further to higher energies, we still decrease now our absorbance. And so really the best place for red solutions to absorb is in that green region. So there's your molar absorptivity piece, right? Red solutions look red because their molar absorptivity is large in the green region, wavelength region. If we then think about concentration, okay, here's a concentration slider bar. So I can start to increase the concentration. If I increase the concentration, you can see my absorbance is increasing as well. And if I decrease my concentration, I start to decrease my absorbance. If I head back to its original setting at 100, I think it was at 100 millimole. Okay, we can now also explore the path length effect. So you can click and hold to drag this and increase your path length. We can go up to 2 centimeters, and now you can see my absorbance is twice what it was at 1 centimeter. If I decrease my path length, I decrease the absorbance of that solution. So in our lab, we're going to have 1 centimeter path length. That is pretty standard on our UV-Vis instruments. You'll have variable wavelengths, but there's only 4 wavelengths that you have access to. You have a blue wavelength, a green wavelength, and maybe an orange wavelength. I think there's 2 blue wavelengths. And so you'll have to choose the best one based on the color of drink that you are interested in. So to sum up here, the molar absorptivity is an intrinsic property. It's wavelength dependent. It's largest when the light is the same energy as an electronic transition in the molecule. So this is dependent on your sample, right? It's dependent on the dye that you're looking at. The concentration for a solution of a fixed path length, the higher the concentration, the higher the absorption. For a solution of a fixed concentration, the longer the path length, the higher the absorption. And in this experiment, your path length is 1 centimeter. And we're going to take advantage of the BEER-LAMBERT law, especially the fact that it's linear, to create a calibration curve. So, for example, if this is the absorption spectrum for a sample that you are interested in, here the absorption is occurring at 280 nanometers, which is actually in the UV region. You can see that as the concentration decreases, the absorbance decreases. So we're going to measure that absorption as a function of concentration to get a calibration curve. So we measure literally, here's one concentration. I'm going to measure the absorption for that. I'm going to do another concentration, measure the absorption for that, and we'll get a linear calibration curve. Ideally, we want to choose a wavelength of the highest absorbance for the greatest range of response. So you can see the concentration range here is giving an absorption response of 0 to about 1.2. That's really as far as you want to go. You don't want an absorbance higher than that, because what that really means is you've got 90% of the light that's getting through your sample, that is being absorbed by your sample. And so if you increase your absorbance above about 1.5, the instruments can't read the light very accurately because there's not enough photons there to read. But you could choose a different wavelength to measure at if necessary. If your colorimeter only has some specific wavelengths and it doesn't have the peak wavelength that you're interested in, you could measure a different wavelength. The main difference here is that it's going to give you a lower slope, so a smaller range of response. So you can see the same concentration range is now only going to about 0.25 or 0.3 on this calibration curve, and that does introduce a little bit of error. From that calibration curve, we're going to get, since it's a linear relationship, we can use line S to get our y equals mx plus b fit out of our calibration curve. And A, the absorption, equals EBC is also a linear relationship. So y on the y-axis is your absorption. Your slope is going to be equal to the molar absorptivity times the path length, and then your x-axis is concentration axis. You may have an intercept depending on how much random error you have in your solutions. But theoretically it should be 0, because if you have no analyte present or no food dye present, you should have no absorption.